Hello, my name is Manuel Maga, and this is a joint work together with Katharina, Kann, and Özlem Çetinoğlu. I don't know if we can fix that we can see the entire screen. Let me see. Somehow. Okay, great. So first, I'm going to talk about subword-level language identification for intra-word code switching, and let's first define what is code switching and the task we are working on. So basically, the definition we have of code switching is that it's a phenomenon of alternating between two or more languages. And as we can see in this example, Spanglish is muy awesome. We can mix different languages into one single part of the chunk of text. So the task we're working on is language identification. That means that we want to identify the language IDs of each token in a code switching context. So what we mean here is that we assign a language ID to each of the words of a sentence. In this case, Spanglish can be interpreted as English, is English, muy Spanish, awesome English, and of course we need also to have some tags for special symbols that we identify as other. Of course there are different kind of variants of code switching. We can find first that sentences in different languages can be mixed into one single text. That means that each of the sentences is in a different language. Then inside a single sentence we can also find combination of words in different languages. And the third one is less studied, and it's when one single word in a sentence can be combined of different languages. So, and this is intra-code switching, and this is what we want to handle in this research. But first let's see why it has not been studied before. We have here the dataset of the Spanish English shared task in 2015. And as you can see, only 4 tokens was labeled as mixed words. That means that, yeah, it was practically not important for such kind of languages. But what about languages that are really morphologically rich? So, and we identified that in such kind of languages, the amount of mixed words is much higher. In this case, we saw that language combination with at least one language is morphologically rich, has this kind of phenomenon, and of course, also in communities that they speak more than one language. So let's have example. This is a polysynthetic language in Mexico. It's called Wixarika. And in this case, we have puti uta kwikwa, and the meaning in English, it's he sang ons. If we change one of the morphemes in this single word, it's a single word as you can see, then, and we substitute it by sing, that is the direct translation, then we see that we have a mixed word, and it is very common in the daily usage of this kind of language of speakers. So this is why we want to redefine the language identification task for code switching. The traditional way of dealing with such kind of words was assigning a mixed word label for this kind of words. But of course, if we do that, we will lose a lot of information. As we see in this example, we are losing a lot of information, and the entire sentence will lose of meaning if we try to ignore this kind of words. So we propose that, of course, the monolingual words should be tagged with a monolingual tags, but we need to split the parts of these mixed words, assigning to each part a different label. In this case, P is Wixarika, cansado is Spanish, and ru is again Wixarika. So we're in our work we're researching on Turkish German and Spanish Wixarika language pairs. Of course, you know all the other languages, but Wixarika is spoken by 40,000 speakers. It's a Mexican digital language, and it's spoken in Durango, Nayarit, Jalisco, and Zacatecas. Belongs to the Uto-Aztec linguistic family, and it's a polysynthetic language. So first, let's talk about our data sets. For the Turkish German data set, we use one that is composed of 1,000 tweets. and 2.7% of the tokens are mixed. That means that 15% of the sentences actually contains mixed words. And in the Spanish Wixarika dataset, it's a little bit higher, with 3%, and 16% of the sentences are also mixed. So that means that these kind of words are really important for those kind of languages. So our input and output and our task is first a couple of words, and then the output we expect to get is also a sequence of tuples of the part of the word, or the part of the word, and the label of the language. In this case, we can see what we expect. We tried out character level by LSTMs, then some pipeline approaches. We first tag each of the words with a hierarchical by LSTM and conditional random fields, and then given the output of this tagging, we split the word with a sequence-to-sequence model or a CRF. The last approach is a segmental recurrent neural network that can do the calculation of the joint probability of splitting and tagging. Okay, for the character level by LSTM, we have a character-based input. Each token of the input is a character. And then we try to predict the language of each of the characters. And after that, if we find that one single word contains more than one predicted language, we can reconstruct it as a mixed token. In this case, with this configuration. Then we have the pipeline approach. First, we use a LSTM or a CRF to tag each word. In this case, the composed word should be tagged as a Wixarika, Spanish Wixarika. Then we have a sequence and then we apply a sequence to sequence or a CRF to do the splitting. And at the last point, we do the reconstruction. So the last approach is a segmental CRF. What is a segmental CRF? First, it's a recurrent neural network. The segmental recurrent neural network is a variation of a semi-Markov conditional random fields. It uses a bidirectional RNN. In our case, we use LSTM that embeds every feasible segment of the input into a continuous space. And as it is a semi-CRF, a segmental RNN defines a conditional probability distribution over the output space. In our case, segmentation and labeling, giving input sequence. So basically, we calculate the joint distribution over a sequence of language IDs tags and the length of a sequence of characters. This F function that we can see, we define it as follows. First, we use LSTM that computes the forward segment embedding by encoding the length of a subsequence of a X starting with SI. And we do the reverse for the reverse direction. Then we have the GY and GZ that are the function which maps the label candidates J in the segment duration set. Then we have also the vector resulting from the concatenation of the previous elements in the parameterization of V and A, and a nonlinear activation function. So basically, it's an end-to-end approach, as we can see here, and it allows us to directly get the output we expect. Let's see some results from these experiments. First, we have the segmental RNN models works better on mixed words. We will show it as follows. Then the pipeline approaches perform better for language pair where the number of mixed words are lower, and mostly on pair on the general picture. And the character level by LSTM do not achieve good results given the large input sequences. Okay, we did evaluation over segmentation and tagging. These are F1 scores. And as we can see, this first chart shows the results on the entire set of tokens. And so basically, the BILSTMs and segmental RNNs work comparable on all cases, with the exception of Spanish Wixarika for tagging, where the segmental RNN achieves better results. But the picture change if we only look at the mixed words. So what we found is that the segmental RNN works much better to handle the problem we are working on. That this means to split and to tag the mixed words. So on Turkish German, on segmentation, Spanish Wixarika segmentation, and Spanish Wixarika on tagging, the segmental RNN works better, and the only exception here is Turkish German for tagging, that again we see a comparable performance. So let's talk about some conclusions we got from this paper. First, we extend the language identification task for code switching to the subword level. We introduce a new Wixarika Spanish code switching dataset. We adapted an existing Turkish-German dataset to set our task, and we proposed a segmental RNN model for the task together with several strong baselines. So we, of course, want to explore normalization on noisy code switch text on the internet to try to get more data sets. Then, of course, we also need to explore not only the surface level, but also some underlying phenomena in the morphology of the word. So this is another thing we want to explore for this kind of languages. And yeah, that is it. Thank you very much, and I'm sure you have a lot of questions.
Okay, thank you. Do we have questions?
Hi, thank you. It's really a very interesting talk. So the question that comes to mind immediately is that maybe my knowledge is out of date, but these sorts of things in sociolinguistic literature often are treated as a phenomenon of borrowing of words into the target language rather than code switching. And also in practical applications in speech recognition, we do tend to just put them in the lexicon. So I guess the question is, do you think that this phenomenon of intra-word code switching is something that's really specific to highly agglutinative or polysynthetic languages, or is it something that you think is more general?
Yeah, thank you for the question. Yeah, the problem here is that the data sets that are available for code switching for languages that are not so morphologically rich, really we can't find so much mixed words examples. This is a problem, and this is why we tried to study languages that are that has a lot of this agglutinative and polysynthetic phenomena, and we found that it is much higher, the rate of such kind of language. The other question is also very interesting. I think that we found that at some point this is integrated, but normally if it's a borrowing of the word, also a phonological adaptation happens. This is why we think that can be distinguished between both of these phenomena.
My name is Brian Cherson, Basis Technology. You worked on pairs of languages. Do you have any thoughts on how you would extend this on an open-ended case where you don't know, where you can say that any language can appear in the middle of any other language's word?
Okay, basically what we found is that pipeline approaches handled very good the case that, for example, the language don't have this kind of phenomena. So, but of course, with the drawback of performing lower for examples like this of the intra-word code switching. But yeah, it's an interesting question. So maybe we need to run this kind of experiments on known data sets and compare how it performs.
It might be it almost never happens. I just thought it'd be fun to look into.
Yeah.
Okay.
Exactly. Thank you.
Okay, thank you. Thank you.
Thank you.